Muted again.
Okay, can you hear me now?
Yes, and now I can see.
Good. Okay, good. So thanks for the introduction, Lydia. So my last name is Gachechiladze. You're not the first one, so don't worry. I usually get surprised when people can pronounce it, but thanks for trying. So I would like to thank the organizers for setting up this nice event and also the Gather Town. It's a pity we couldn't meet in Gdansk. I would follow what Marek said. It's really indeed a beautiful place and it has become very close to my heart in the last year. So I would encourage all of you to go and visit Gdansk one day if you haven't yet. So back to the topic. Today I'll be talking about quantifying causal influence in the presence of quantum common cause. This is joint work with Nikolai Miklin and Rafael Chavez. So I've planned my talk such that I don't have to rush to the end. So please interrupt me if you have any questions, like if you don't want to write it in the chat, also you can stop me. So this is the outline of my talk. I'll just give a very brief introduction of what I need from causal modeling in the classical case in the beginning, and then we will quantize it. And then the main part of the talk will be discussing how to measure a strength of causal influence in classical causal structures. So this will be like, we'll be taking certain measure of the direct link of causal influence, and then we will be quantifying this measure. And there are already these tools available. This in the classical causal inference, this is known, and then we will see whether this goes through if we have the quantum common cause, whether things still work there. And I will tell you about our results in this direction. Okay, so to start with the introduction, so usually when you have observed variables which are correlated with each other, deciding cause and effect relationship between them, it's not an easy task. And it's one of the central tasks in the science because we are interested into such relationships. So if we have correlations between two variables, let's say variable A and variable B, variable A could, for example, be smoking and variable B can be cancer. Then Reichenbach's common cause principle tells us that there could be one of the three relations between them. And these variables I'm going to be drawing as vertices in this directed acyclic graph. And the causation between them I'm going to be drawing as a directed link. And we can be saying that in the two correlated variables, variable A might be causing variable B. And in this case, we will be drawing a link between them, or it can be other way around. For example, cancer could be causing smoking, or there can be the third case when there is a hidden common cause, for example, genetics, which could be guaranteeing that you will be addicted to the smoking, but it will be also that you have a cancerous genes. So these are three possibilities. However, today we will be interested in a more complicated scenario when you have two possibilities. So you don't only have a direct link from smoking to cancer, let's say, but you also have a common cause between them. And the question that we will be asking in this particular case is, can we actually quantify how much smoking causes cancer in the presence of unobserved common causes? Okay, so we are interested in the strengths of the causation from A to B. And in order to do so, there are already known techniques. So there is technique in causal inference, very useful technique called interventions. So what happens now in the interventions is that if we have a causal structure on the left-hand side, we can go ahead and intervene in the variable A, and we can just give it force it to take a value, certain value. Okay, as a result, this erases all the links from lambda, which is a common cause to A, because we have forced it to take the value, so it becomes independent of all its parents. And then we can see how B changes as a result of this intervention. Let me now formalize this. So if we had a joint distribution of the joint probability distribution for the left-hand side, on the right-hand side, we can actually define the do probabilities. So this is what we are going to be calling, what is the probability of Bob's outcome conditions that we intervened on Alice's outcome. And I mean, this is different from the conditional probability. You can think of it, and you can also see how it's written in terms of the probability distribution, but it's not the same matter as just the conditional probability B conditioned on A. And also in this talk, I'll be using this notation everywhere that the capital letters will be random variables and the smaller letters will be the values. Okay, so now that we have already defined the two probabilities, which again, just to emphasize one more time, what it does is that it looks at how sensitive B is on the interventions of A. We can look at the measure of causality, which we call average causal effect. And this measure of causality checks exactly the sensitivity of B on the different possible interventions on A. So you have to maximize these interventions and take a difference, and this is the average causal effect. So you can actually calculate this in the experiments. You can go ahead and intervene on certain data, but it's not always ethically justified. For example, you cannot force somebody to smoke in order to see whether they will develop cancer, or you cannot force somebody to stop smoking right away. But there is even more conceptual problems. Interventions are not always possible. So you cannot intervene, for example, in the data which you have from the past. So now the question that one asks here is that can we actually estimate this average causal effect in some other ways without an intervention? Can we just have the probability distribution from the past experiment and actually say this is how much A was influencing B? And luckily, there is already the framework devised for this matter. And to do so, we have to introduce additional variable in the causal structure, and this is called an instrumental variable. Instrumental variable is in the full control of the experimenter, and we are assuming that it has only a direct link to the variable A. So for example, X could be the taxation of tobacco, and A is smoking. And we believe that X doesn't have direct influence on cancer, or it's independent also. We are assuming that it's independent of lambda, so it's independent of the common cause, which is, for example, genetics. And also this will be the statistics observed in the instrumental scenario. Okay, so the statistics are compatible with this instrumental scenario. It's decomposed according to the diagram. So now how does this help? How does introducing this new variable helps? So let's consider the example. Let's consider such an example that B is linearly dependent on A. And if this is the case, kappa here corresponds to the strength, how much A is influencing B. And if we want to estimate kappa, then it would be very simple, because what you can do, you can take the covariances on the both sides. And because we know that lambda is independent of X, you can directly estimate kappa in such an instrumental scenario. But one can go a step further. So you can, we don't want to have such assumptions. So what Pearl has devised in the simplest instrumental scenario with binary inputs, all the binary variables, what one can show is that there exist certain device-independent lower bounds to average causal effect. So this is obtained using linear programming, and this is expressed in terms of only observed probabilities. So it's kind of a very important result. It's one of the seminal papers in this direction of causal inference, where it tells you that you can actually, from the observed probabilities, lower bound this direct link. So now the question that we will be asking, okay, we have this result, but what can change if we have a quantum common cause? If we replace lambda with the quantum common cause in this instrumental scenario. And everywhere in this talk, I'll be assuming that we have binary variables. Okay, so let's now move into the quantum realm, and let's see how we define this quantum common cause and quantum causal structure. So here we will be assuming that there is a quantum shared state instead of lambda, and the variables are again classical variables. So we will be obtaining them via making measurements on this quantum state. Okay, so you can be obtaining the following probability distribution. So now the one common quantum common cause structure that you have seen very often is the Bell scenario. In the Bell scenario, what you have two separate inputs, and you have the following distribution. And one thing I want to emphasize here, the output of Alice is independent of Bob's input. So there is this free will assumption on, there is no communication between them. But in the Bell scenario, we are always asking this question, whether we can actually distinguish if we had a classical common cause or quantum common cause, and there are these Bell inequalities, which all of you know. But now what we can do, we can go back to the instrumental scenario. And now quantum instrumental scenario, you can think one way as just generalization of the classical one, but on the other hand, you can also think it as a relaxation of the Bell experiment, in a sense that Bob doesn't have free choice anymore, but instead there is an input from Ali. Alice is determining Bob's input. So in this case, if we look at the probability distribution, there is no Bob's free choice of the measurement anymore because it's determined by Alice's input. And so this is a bit more relaxed scenario. So now the further question that one can ask is that, are there Bell inequalities in the binary simplest instrumental scenario? We have 2 inputs and 2 outputs. Can we have Bell inequalities which will distinguish classical for quantum set? And it appears the answer here is no. Actually, there is only a simple one single inequality, which is an instrumental inequality, and it is valid independent of whether you had a lambda or shared quantum state. So what this tells us is that set of correlations, actually in the simplest instrumental scenario with binary variables, they coincide exactly with each other. So this could tell us that there might not be any device-independent way to decide whether you have a classical or quantum state there, but this is exactly what I'm going to be addressing in the rest of the talk. And there is indeed a way to device-independently certify, even though there are no Bell inequalities, that there is a quantum state shared between these two variables, between A and B. So in order to do so, I have to go back to this average causal effect and this discussion of the lower bounding average causal effect. So for this, the first step I have to do, I have to introduce how to do interventions in the quantum model. So on the left-hand side, now you see just the Born rule written, and this is how we calculate the probabilities in the instrumental scenario. In the right-hand side, now I'm going to tell you how we do interventions. So in order to do interventions, again, we are forcing Alice's outcome to take certain value, but as you see, there is no direct link from row AB to A. So Alice is not making any measurement anymore. Instead, what's happening is that Bob's measurement is determined by this intervened variable. And as a result, there is this partial probability, or you have to trace out one of the parties. And this is what the do probability, how the do probabilities are defined in this realm. You can again notice that this is different from summing up over Alice's measurement on the left-hand side, because if you change Alice's output, Bob's input will change. So this wouldn't give you the partial trace. So do probabilities are again different in this particular case. And now we can write down the average causal effect calculated using quantum state. And it's again a difference between 2 do probabilities. So it's exactly the same as it was for the classical case, but now it's written using the Born rule. Okay, so now I have given you all these details, and now comes the first slightly surprising result in this direction, which was given by Rafael Chavez and his collaborators. And for this, I have to a bit summarize what we have seen. So what we have seen by now is that we had in the simplest instrumental scenario, there is no differentiation between the sets, whether you had a classical set or quantum set. And we have also seen that there is in the classical causal structure, there is this lower bound that we have. So now what Rafael showed is that this lower bound no longer holds actually if we had a quantum shared state. So now, because we are in the binary setting, we can just stop maximization, because we can just have the absolute value, and this would be taking care of the maximization. But this is a definition of average causal effect. It just simplifies for the binary case. But let's look at the example. How can we see actually that this can be violating the bound? So let's consider the example where we have, for example, a maximally entangled state, which will have the maximally mixed marginal. So Bob will always have the maximally mixed marginal, so something proportional to the identity. But if then Bob chooses to make measurements, which are projective measurements, the difference of these two projective measurements will always give the answer 0 in average causal effect. But note that I haven't really specified what the measurements are in Bob's case, or we haven't even said anything what Alice's measurements are. So you can think of this way, you can go ahead and now make sure that your right-hand side of this lower bound will always be strictly greater than 0. And in this case, you're violating the classical lower bound. Okay, so I mean, I don't give you here the example, but you can think of it as you have too much freedom to do that anyway. So there are examples where you can just write this probability distribution compatible with maximally mixed marginals, which will be strictly greater than 0. So here now we see the violation. So what does this mean? Just to summarize, what it means that even though the set of observed correlations in the simplest instrumental scenario is the same for lambda and rho AB, the causal differences, dependencies are very different. So we have to treat them differently from one another. So then the first natural question that we asked in this direction, which other states and measurements lead to the similar violation on average causal effect? And the second question is, can we actually devise a lower bound which is valid for the quantum case? So now these are the two questions that I'll be answering in the rest of the talk. Okay, so the first question has a very intuitive answer. That's something that you expect from the quantum non-locality. And the first result is about the states. And it tells you that every pure entangled state can generate correlations that violate the classical bound on average causal effect. This is exactly what you expect in a non-locality. And moreover, entanglement is necessary, but not sufficient for such violations. So this is not maybe very surprising, but what we can see here, which is slightly more surprising from the perspective of non-locality, is that if you take, for example, the parametrization of 2-qubit state, you can actually optimize the violation and you can draw a curve with respect to this. Alpha is the parametrization from 0 to pi over 4, where pi over 4 is the maximally entangled state. And here you can notice that maximally entangled state doesn't give you the maximum violation. The maximum violation is actually obtained on some other weird angle. So this is known as an anomaly of entanglement. Some people have named it like this, but yeah, this is one of the results that you can show that maximally entangled state is not the best. So the second result in this direction concerns the measurements. And here we showed that every pair of incompatible rank 1 projective qubit measurements can generate correlations that violate quantum classical bound on average causal effect. And moreover, incompatibility is necessary but not sufficient for such a violation. And here again, what we have a curve where this is the angle between Bob's measurements, and then this is the optimized violation. And again, this optimum is not obtained for mutually unbiased basis. It's obtained for this other angle. If you wish, you can call this anomaly of incompatibility, but yeah, this is what we see in this violation of average causal effect. So at the moment, we've seen that average causal effect in classical and quantum scenarios must be treated differently. But the main question that we answered in this, we ask here is that can we actually have quantum lower bounds? And this is actually not as easy to derive as it was in the case of classical causal inference, because we cannot use linear programming anymore. Okay, so one has to think how to get actually such lower bounds. And first I'll show you the lower bound, and then I'll tell you how we have proved it. Okay, so quantum lower bound looks as follows. It doesn't look as pretty anymore as it was in the case of the classical case. But you can again see that it's a nonlinear expression in terms of the observed correlations only. Okay, so I don't expect you to stare too much at this expression and memorize, but I think it's more important to see how one can derive this bound. And so we have given some slices here, also in the space of correlations. We just give one of the slices where there are 3 different lower bounds given. So here, this C, Q, and N indicate classical quantum and non-signaling lower bounds. And this is the space of, this is a slice in which you can see that this blue region, light blue region, is the region where classical average causal effect gives you non-zero, non-trivial lower bound. And the red one is where the quantum average causal effect gives you non-trivial one, and the region is smaller, as you see. And this dashed line is the case for non-signaling. So we also in the paper give the full characterization of the lower bounds for the non-signaling case. However, I haven't presented it in the work. We can discuss it later if you want, or you can also read the paper if you have questions about it. But now let's go ahead and see the proof, how the proof works. And before I go there, if there are any questions, I can also answer, because I think I have enough time for the proof. It's just a sketch of the proof.
I think we can have questions at the end. At the moment, there's.
Okay. Good. Then I'll leave time for the questions. Okay, so let's see how one could prove how one can derive such a bound. So the first step here is to actually map the instrumental scenario back to what we know, back to Bell scenario. So what we do here, we express every correlation that we need into deriving this bound using the Bell scenario. Okay, so instead of just writing this one, we are going to write it, we are going to express it in the Bell scenario, and this one can do the same exact thing for the do probabilities. Do probabilities, again, was just tracing out one of the parties, so you can sum up over Alice's measurement outputs. For the Bell case, I mean, it was not tracing out for the instrumental, but in the Bell case, you can just express it in the following way. So now the second step is to just consider a generic Bell expression. Okay, so we have just written down some linear combination of the correlators that you have in the Bell expression, where alpha, beta, gamma, and delta are some real numbers. As a third step, you can go ahead and express this Bell expression using the probabilities that we have in the instrumental scenario. So you can just translate it in terms of the probabilities and do probabilities. So now we can go ahead and fix certain values of alpha, certain value of gamma and delta in the following way. If you take these two values, you can notice that on the right-hand side, you are obtaining the difference between two do probabilities. And that's a good thing, because that means this is average causal effect. This is exactly what you wanted to express. So as a fifth step here, we can go ahead and we can use the bound on this Bell expression, which is the following bound. And then you can optimize over the values of alpha and beta in order to reach the best possible lower bound of quantum average causal effect. And this is indeed what we have done, and this is how we have obtained this lower bound. Okay, so this is again going through the well-known Bell steps in order to reach this lower bound. So we are not sure how tight this lower bound is. It would be nice to actually derive maybe better lower bounds, and like we tried many other methods, and this was one of them which worked, but we are open to discussions, like if somebody has any idea to derive better lower bounds or to generalize these results. So please come to us and in the Gather Town and talk to us about it. And yeah, this actually brings me to my conclusions. So what we have seen today, so our results are that causal reasoning is very different in quantum mechanics and also in the non-signaling theories correspondingly. We have seen that one can violate the classical bound of average causal effect. And this can actually, violation of the classical bound on average causal effect can be used to witness in a device-independent way entanglement and incompatibility. And this is using different device-independent scenarios than Bell inequalities. So it actually really utilizes this definition of average causal effects. So it's a different signature of device-independent witnessing than the one most used in the community. And finally, we have devised the lower bounds also for quantum common cause, which proved to be much more difficult than in the case of the classical one. The work in progress at the moment, we are working on experimental realization to actually prove this lower bound to see how well it works, and also these violations that we want to observe in certain experiments. And another thing that we are doing, we are considering measurement dependency in the instrumental scenario. There are this relaxation of free will assumptions also in the Bell scenario. Here we have this relaxation already available, but one can also consider what happens if the instrumental variable has some dependence on lambda. What if this instrumental variable, like